of 200, and you would never be asked to do a problem like this, but you would be expected to know, okay, I've got to know my prime numbers here, 2, 3, 5, 7, and so on. And you start with the smallest prime number, 2, and you build this factor tree. Now, what I didn't tell you that you could do is you can stop when you get a perfect square. 100 is a perfect square. Okay, so this actually tells you that the square root of 200 is really the square root of 2 times the square root of 100, which is the square root of 2 times the square root of 100. This part is 10, so this becomes 10 root 2. So what some students do is they say, I'm going to look for the biggest square root that goes into a number. Okay. And so you might think, well, that makes sense. Like I can do that. And it works for problems like, let's say I give you the square root of 300. Well, you might immediately say, oh, well, that's 3 times 100, square root of 3 times square root of 100. So that's 10 root 3. The question is, how quickly can you determine the largest perfect square that goes into a number? And it really depends on the problem that I give you. So like maybe you will see it for this problem. What is the square root of 75? Well, if you start with the prime factorization, you say, well, 2 doesn't work, but 3 does. 3 times, what number goes here, Julia?
25.
25, and that's a perfect square. So we can stop. We say, oh, that's the biggest one. So because this is the square root of 3 times the square root of 25, so it's 5 square root 3.
Okay.
You might think, well, why didn't you show me this before? Well, you can look for the biggest one. It does work, but you got to be careful. So let's say I give you a much more complicated problem like this one. What is the square root of 350? So what would you do here? Because you can do it the way that I suggested, which is this prime factorization. You can say, well, what's the biggest perfect square that goes into 350? And your perfect squares are 1 squared, 2 squared, 3 squared, 1, 4, 9, 16, 25, and so on. But you got to find the biggest one. And that's really the challenge. So what I would suggest is kind of like most things, it's a combination of the two. Like start with the prime factorizations. This is 2 and 175, and then 2 doesn't work again. 3 appears to work, but it actually doesn't. So the rule for 3 is you have to add the digits and see if they add to a multiple of 3. So 1 plus 7 plus 5, that adds up to 13, which is not divisible by 3. So we move to 5. 5 goes into this how many times? Well, that's where it's a little bit, gets a little bit harder, but it ends up being 35. And so you try 5 again, you get 5 and 7. So the second approach, where you try to look for the largest perfect square, you may struggle with a problem like this one, because the answer, you have these two 5s, so you can bring the 5 out. 5 square root of 2 times 7, or 5 square root of 14. And that's why this traditional approach seems to work all the time. But if you were if you're just on on that day, you just say, oh, I got it, you might figure out pretty quickly that 25 goes into this, but how many times? Well, 25 goes into 100 4 times, and there's 3 of those, so that's 12. 50 is 2 more, so that's 14. So you might be able to do this and very quickly get to the same answer. So let's have you look at a less complicated problem. Let's just see if you can, and you get to choose which strategy you use, but I want you to try the square root of 60. And either build a factor tree or look for the biggest perfect square that goes into that number. So go ahead and try that, and then I'll check back with you here in a moment or two. How are you doing on this one?
I got 2 square root 15.
Okay, and that is correct. And I know it's correct because I square this number and I multiply it by the number inside, and that's 4 times 15, which is 60. Yes, that's correct. So I'm not sure which approach you used, but the only way to kind of figure out which is going to work best is to do a lot of practice. This is a large number that, you may or may not see the biggest perfect square right away in. First, and this is important, you truly do want to start with the smallest prime. You don't want to go right to a bigger one, even if you know that it works. So 2 and 99, 3 and 33, and then 3 and 11. So at this point, once I've built the tree here, whenever you see the pair, that's when you should just say, should I have seen that from the beginning? Should I have recognized that 9 was the biggest perfect square? So the divisibility rule for 9 is you add up the digits, and if it is a multiple of 9, which this one is, then it does work. And that's when it is okay to go ahead and say, oh yeah, it's 9 times, well, whatever it is here, 22 it looks like. And that's where you save some time if you want to try and master some of these strategies, but this one will always work. It's just a little slower in most cases.
Okay.
So let me have you try one more or two more here. Maybe try maybe a little bit more difficult one. Let's go square root 264. So go ahead and try that and let me know when you've got an answer, please. How are you doing on this one?
I did the factor tree and it's definitely a lot slower.
It is. So 2 and 132, 2 and what'd you get here? 66.
Mhm.
Okay. So this is the point where you might say, like, should I have just tried a bigger number, like 4? And sometimes you don't know until you're all the way done here. The problem is that it is 4. So you don't save a ton, but you do save the time from writing this out, because time is obviously working against you when you're doing this. Um, so there's a worksheet that I'll send you, and after the lesson, in the email, and you can try more of these. But I want to move to some problems that that you will see on the standardized test that are kind of based on this. We need to do just a tiny bit of review here. What is the square root of x to the 8th? Do you remember how to do this problem, the square root of x to the 8th, how to reduce this?
Not really.
The square root of x is really x to what exponent? Do you remember that?
Oh, 1/2.
1/2, perfect. Okay, so when you see the square root of x, you want to think x to the 1/2. So this right here on the left is really, and if you think about where the numbers came from, the 1 is in the numerator, the 2 is in the denominator. This is really x, and there's a 2 here. It's 8 divided by 2, which is x to the 4th.
Okay.
Okay, so like, let's say I asked you for the 4th root of x to the 16th. What would you tell me based on the previous problem here?
X to the 4th.
Yes, because it's x to the 16 divided by 4, which is x to the 4th. Okay. Now, where this gets a little bit more complicated is what happens if it doesn't divide perfectly. And this is, I'm sorry, this is where we're starting to move into that standardized test stuff. So there are two possibilities. The first is that this is x to the 3/2 power, just like the previous problem. Do you agree with that?
Yeah.
Okay. And then here's how it could also be written. This is what we were doing before. X to the 3rd is really x squared times x, which is really square root of x squared times x, square root of x, which is x times the square root of x. So these are equivalent. They are exactly the same.
Okay.
Which do you like better? The one on the left or the one on the right?
The one on the left makes a little more sense.
And the one on the right is the one you see on standardized tests. So that's the
Oh.
problem there. That's the issue. Is you have to realize that it's the same thing here. Okay.
Okay.
Was working with a student who's a basketball player, and we talked about the idea of like zone defense versus one-on-one defense, and they're the same defense, but they can appear differently, and that's you've got
Mhm.
to somehow you've got to say, okay, I've got to be willing to accept that there are different ways to see this for the same thing, and be able to work through it. So let's try another problem here. This isn't a skill you just learn. You do one problem and you get it. Let's say it's the cube root of x to the 4th. So we know that this is x to the 4 over 3 power.
Mhm.
Okay. Similarly to the square root problems, it's the cube root of x cubed times the cube root of x. So whatever the number is above the root, that always is there. And then you break the exponent into the numbers that add up to it. And what you're looking for is when these match. Because when they match, it becomes just x times the
Okay.
cube root of x. Now, just to go kind of backwards to just fully confirm this right here on the right is really x to the 1/3. And this on the left here is x to the 1. When the bases are the same, you add the exponents. What is 1 plus 1/3? Well, if you make a common denominator, it's 3/3 plus 1/3, which is 4/3. Okay, so let me have you try one here. What is the 5th root of x to the 6th? Give me the two forms, give me the two ways that it could be presented. How are you doing on this one?
So I got the first one and I might have gotten the second one. I don't know.
So
Um,
the second form would be x, the fifth root of x. Is that is that what you have, or do you have something different?
I kind of got there, but I don't know. I'm still confused just a little bit.
Okay, so we're gonna just kind of do a few more variations. Let's say we want to do the square root. I'm sorry, the cube root of x to the fifth. Okay, and we really need to start working with this second form. So this is the cube root of x cubed times the cube root of x squared. So whatever the root is, you keep that there. And then cubed and squared, okay, they have to add up to 5. And again, the analogous problem here is it's like the root problems we were doing earlier with numbers. And obviously there's a big difference because it's variables versus numbers, but hopefully you can see where the 5, the 3 and the 2 and the 5 go
Mhm.
together. So when these match, it just becomes x because it's literally 3 divided by 3, which is 1.
Okay.
The 2 is less than the 3, which is why it becomes x to the 2/3. But for our purposes, we're writing it this way. So let's try another one. So let's go with the fourth root of x to the 7th power. So this is the fourth root of x to the 4th times the fourth root of x cubed. The 4 here and here in the root part is because of that root there. The 4 here is because we want it to match this 4 and 3, and the 4 plus 3 have to add up to 7.
Okay.
So on the left, this just becomes x, but on the right, because the 3 is less than the 4, because there's not enough x's to get one to come out, that's why you leave it as the fourth root of x cubed.
Okay.
Let's try another one here. Let's say we're gonna make this a little bit more difficult. So let's say it's x to the 12th. So this time it's the fifth root of x to the 5th times the fifth root of x to the 5th times the fifth root of x squared. And you're probably thinking, well, where did those numbers come from? Hopefully the top one is clear now. It's always whatever the last one is. So what
Mhm.
we really want is the match. We really want the 5 and the 5 to match. The 5 and the 5 to match. And we want the 5, and the 2 to get up to 12. So this becomes x, and then the fifth root of x squared, which becomes x squared times the fifth root of x squared. Now I may have lost you, and that's why we're going to do it this other way. You're going to take the 12 and divide it by 5. And if we went back to elementary school math, you would say that that is 2 with a remainder of 2. Do you agree with that? 12 divided by 5 is 2, but there's 2 left over.
Yeah.
The first 2 goes there. The second 2 goes there. So let's go back and look at an earlier problem that we did and see if we can apply this same approach. So we did something like the fifth root of x to the 6. So this is really 6 divided by 5, which is 1 with a remainder of 1. So this becomes x to the 1, fifth root of x to the 1.
1.
So I think you're starting to see this here. Let's say it's the 8th root of y to the 20th. This is y, it's really y to the 20 divided by 8. And 20 divided by 8 is 2 with a remainder of 4.
Okay.
Because 2 times 8 is 16, 20 minus the 16 gives you the 4. This becomes y squared eighth root of y to the fourth power.
Okay.
So let's say I wanted the square root of 32. 32 is really 2 to the fifth. And there's really a 2 there. Do you remember? Do you agree with that when it's a square
Mhm.
root? So this is 5 divided by 2. 5 divided by 2 is 2 with a remainder of 1. So it's 2 squared, square root of 2 to the 1, which is 4 root 2, which is exactly what you would have gotten with this approach over here on the left.
Okay.
Because you would have pulled out a 2 twice, and had 1, 2 left over inside. So the shortcut here is you take whatever this is and you divide it by that. You figure out how many times it goes in and whatever is left over. So let's have you just try a couple problems here to see if it's making any sense. Let's do the 7th root of x to the 12th. And then let's have you do the 4th root of x to the 23 power. I'd like you to work on both of these for me, please.
Okay.
How are you doing on these problems, Julia?
I think I got it.
All right. So the approach we talked about is you would take 12 and divide it by 7. This is 1 with a remainder of 5. So you take that x, whatever this is, and you put it to the power of 1 here. It's still the 7th root. That 7 comes there, x to the power of 5. Is that what you have?
Yes.
Perfect. Okay. So similarly over here, we would have 23 divided by 4, which is 5 with a remainder of 3. So that becomes x to the 5th. The 4th root of x to the power of 3.
Okay, that's what I got too.
Perfect. Okay. So the reason we're doing all this is not because this is important in math. This is because it's important for standardized testing, because you get a problem like this. You'll get a problem like 2 to the square root of 32 divided by 8. And it'll say simplify. Okay. And so I may have lost you already, but this is the kind of question you actually can do right now. So if I were to just, and we're starting with numbers, if I were to just ask you to do this part right up here, okay, the square root of 32, you would be able to reduce to 4 root 2. So far you could write this as 2 to the 4 root 2 over 8. And that answer would not be there. So you'd have to go a little bit further. 8 can be written as 2 to the power of 3.
Mhm.
And from here, we have to introduce some new stuff, which is, what do you do when the bases are the same and you're dividing? You subtract the exponents. So here you might write 2, 4 square root 2 minus 3. And that would be the final answer. So let's look at another problem. Let's just keep kind of trying to work on this. So let's say it was the square root of x to the 7th divided by the cube root of x to the 4. And it said to simplify this.
Okay.
So I want you to simplify the numerator. What did you come up with for the numerator?
I got x to the so I got 3 remainder 1 when you
Right.
divide it. I got
Okay.
x to the 3rd times, how do you say it? It's 2 root, right?
The square root of x, or 2 root x. So with the square roots, with the 2, you just say square root like that. Good.
Yeah.
Good. Now in the bottom, if you do the same thing, you would say, okay, 4 divided by 3 is 1 with a remainder of 1. So that becomes x cube root of x, like that. Okay. Unfortunately, there's no way this would be the final answer. Okay. So in full disclosure, this problem I gave you, you actually don't want to do it the way we've been doing. You want to do it, and you might think, well, come on, Matthew, like this is confusing. Well, you got to be able to do it both ways. So this is 7/2 over 4/3. When the bases are the same, you subtract the exponents. So let's subtract the exponents here. Let's make a common denominator of 6. So that's 14 over 6. I'm sorry, 21 over 6 minus 8 over 6. So that is 13 over 6. So your answer is x to the 13 over 6 power. And that's where you do want to do the thing we've been doing, which is to take 13 and divide it by 6, which is 2 with a remainder of 1, and your final answer would be x squared because of that. The 6 tells you the root, the 6th root of x. And this likely would be how the answer is presented.
Okay.
So sometimes you got to try the problem one way, say, that's not really doing much, and then go the other and see if you can get there and figure it out. So let's do another one. Let's see if we can. And so assume I want your final answer like this, but I want you to work through with the exponents this time. So let's say I give you the square root of x to the 9th divided by the 4th root of x to the 10th. I'd like you to simplify that, please. How are you doing on this one?
I think I got it. I'm still just like a little bit confused.
Okay, so the numerator we can write as 9/2 power because there's really a 2 there. The denominator is 10/4. Okay. Now you could, and you can always simplify fractions. So like what I can't do is I can't cover like all the possible cases because but this becomes 5/2. And then when you subtract the exponents, I was trying to make this one even easier than the others, is you just get x to the 4th when you're all done.
Okay.
Now let's say it was more like the problem we were previously doing. So let me just let's just change the numbers here a little bit. Let's go cube root of x to the 10th here. So this would be x to the 11/2 over x to the 10/3. Okay, and this is where you subtract again, but you don't have a common denominator, so you can't just get a nice number like you do here. That common denominator is 6. That's 33 minus 20. So again, you get that 13/6. x to the 13 over 6 power. That's where you divide if you want. You get 2 remainder 1, so it becomes x squared. And then this 6 on the bottom becomes the 6th root of x, like that.
Okay.
The point of all this, of course, is that there's just a variety of ways to show the same thing that you actually know. You just need a little bit of a refresher. So let's say I wanted x to the square root of 1 over 100 divided by the square root of x. How might we handle a problem like this? Well, you're going to use some of the approaches that we've been doing thus far. The added little wrinkle here is just, how do you handle this up here? Well, you can also, and this is again one of those like, well, it's up to you how you can just take the root of the top and the bottom. The square root of a over b is the square root of a over the square root of b, which makes this 1 over 10. So the numerator is x to the 1 over 10. The denominator is x to the 1/2 power. So it's all about manipulating like these expressions into something that is more familiar to you. So this you do know how to handle. You know to subtract the exponents, 1/10 minus 1/2. So that's make a common denominator here, becomes 1/10 minus 5 over 10, which is now negative 4 over 10. Sorry, let me grab that. You can simplify the fraction so that it becomes x to the negative 2/5. And there's another exponent rule to think about. If you have x to a negative exponent, it becomes 1 over x to the exponent. So we can write this as 1 over x to the 2/5 power. And then this time the number on top isn't bigger, so you don't divide because it's only the case when it's bigger. So this becomes the 5th root of x squared. And this again could be one of the ways that the answer could be written. Let's have you try another problem here. So let's have you try x to the square root of 1/4 divided by the 5th root of x to the power of 1. Let's try that. So I'd like you to try simplifying this one, please. How are you doing on this one?
I started it, but I'm a little confused on how to finish it.
Okay, so you take the square root of the 1/4, that's the square root of 1, square root of 4, that's 1/2. So the
Mhm.
numerator is x to the 1/2. In the bottom, we can write it as x to the 1/5. Since the bases are the same, you subtract the exponents there. So you got to make a common denominator here. 10, we'll say, so that's 5 over 10 minus 2 over 10, that's 3 over 10. So the answer is x to the 3 over 10, but it could also be written as the 10th root of x cubed. And today is all about, do you see that? Do you see that? And then would you be comfortable moving between them? Well, that comes with a little bit more practice for that. So like most standardized test questions, there's always kind of a synthesis of steps. You've got to know how to deal with roots. You've got to know how to deal with exponents. You got to know how to deal with the exponent rules and somehow get an answer that matches. I mean, there's maybe even a third one here. It could be x to the 0.3 power. Excuse me, because that's 3 divided by 10.
Mhm.
So that does take us to the end of our lesson for today. We've got another lesson tomorrow, so we'll just pick up and do a bit more on this. If you got some time, I definitely recommend trying that reducing roots worksheet. I think it'll help out, and we'll just keep working on these skills that are going to help you be successful on the SAT.
Thank you so much.
You're welcome. Have a great day. See you tomorrow.
Bye.